In this video, we're going to revisit many of the feature engineering steps that you can undertake depending on the machine learning model you're building, to pre-process your data and leave it suitable to use to train machine learning models and make predictions. So why do we need to engineer our features? There are a variety of problems that we can find in the variables in our datasets. One of the problems is missing data. This is the absence of values for certain observations within a variable. A second aspect that we need to tackle is the presence of labels in categorical variables. This is, the values of the variables are strings rather than numbers, and we can't use them as such in machine learning models, certainly not in Python using scikit-learn. A third consideration to keep in mind is the distribution of the variables for numerical variables, and specifically whether they follow a Gaussian distribution or if they are rather skewed. For some algorithms, the presence of outliers is also detrimental. Outliers are unusual or unexpected values within a variable. This is values that are extremely high or extremely low compared to the majority of all the other values for that same variable. So missing data, as I said, is the absence of values for certain observations within a variable. And it affects, of course, all machine learning models, in the sense that we can't really feed observations to a machine learning model that contain missing values, not if using scikit-learn at least. So there are a variety of reasons why data could be missing. A value can be lost or not stored properly, for example, during data storage. Or the value does not exist, for example, if the variable comes from the division of two other variables and the second variable takes the value 0. The division by 0 does not exist. Or if the data was obtained from a survey, say, and the person refuses to answer a question, that could also be a missing value. So we need to be prepared to fill in those missing values with some sort of number to use in machine learning. A second problem I mentioned is the presence of labels or strings in categorical variables. These problems come in three flavors. The first is the cardinality of the variable. And by cardinality, I mean the number of different labels or categories that the variable can take. In fact, variables with big number of categories tend to dominate over variables with smaller number of categories at the time of building machine learning models. And this is particularly true for tree-based algorithms. Tree-based methods tend to overfit to variables with high cardinality. A second problem is the presence of rare labels. Rare labels may also cause trees to overfit, but most importantly, they represent an operational problem because they are rare. Some of these labels, because they are rare, because they are infrequent, because they are present only in a small proportion of the observations, will appear only in the training set, and some of them will appear only on the test set. So the model will not know what to do with those labels that are present only in the test set and have never been seen during training. So this step is extremely important at the time of model deployment, because it involves additional steps that we need to take to tackle unseen values. We will show you more on this in a dedicated section. And finally, for categorical variables, the presence of labels themselves, this is the presence of strings when we actually need numbers to fit machine learning models using scikit-learn, is something that we need to address in a step that is called categorical variable encoding. Speaking of numerical variables instead, what we normally consider when building machine learning models is the distribution of the variables. A better spread of the values over a larger range tends to improve the predictive performance of these algorithms. We also mentioned outliers. What are outliers? Well, if you remember, outliers are values that are extremely low or extremely high compared to the remaining values for that variable. Outliers may affect certain machine learning models. You're probably familiar with how an outlier may affect a linear regression. Look, for example, at this illustration here. You see clearly how the presence of the outlier deviates the straight line from what otherwise seems to be the relationship of the majority of the values with the target. And there are other algorithms that are sensitive to outliers as well. Think, for example, AdaBoost. AdaBoost is sensitive to outliers because this algorithm puts tremendous weights to the outliers as the different trees are built to try and correct the prediction that the previous tree made wrongly, and this tends to cause overfitting and a bad generalization. And finally, the magnitude of the features affect as well model performance. Think, for example, in a length variable. If the variable is in meters and we change it, we transform it into kilometers, the coefficient that multiplies that variable will also change if what we are building is a linear model. From a different perspective, if we're trying to predict house price and we have one variable that is the area in tens of square kilometers, and a different variable is the number of rooms that varies from 1 to 10, in a linear model, the variable that takes the larger values will have a predominant role over the house price. So in this case, the area variable will be more important to determine the price of the house. However, we know that the number of rooms also plays a role. So what can we do to make that variable count as well? In fact, most of the algorithms are sensitive to scale. If you look at this slide, I have listed those algorithms that for one reason or another are sensitive to the magnitude of the variable. So linear models, we've seen why, but also support vector machines and neural networks are supposed to converge faster and find the optimal hyperplane faster when using features with a similar scale. And of course, all the distance-based algorithms are also sensitive to the scale of the features.